Welcome everyone. Myself Dr. Kumar, a lecturer in NAS, Center for Theoretical Physics and Natural Philosophy, Mohidolo University, Nakhon Sawan, Thailand. Today we will be discussing about second quantization in Fock space. So it is about how you obtain a second quantized theory from a first quantized or quantum mechanical theory. So a prerequisite of quantum mechanics is expected from the audience. So let's proceed. Quantum mechanics is all about microscopic particles, their interactions. So what we observe is that these microscopic particles have zero size and mass and other aspects, but they are point particles and they interact with each other through direct interactions, which are called as discrete interactions also. And they are defined by something called a wave function, which is a local probability distribution. That means it represents probability of finding the particle at a particular point in space and time. However, we end up with systems in real life which have infinite degrees of freedom. They are not made of point particles. They are continuum in nature, and also sometimes the amount of matter or the number of particles is not conserved also. Many a times particles get created and annihilated. For example, the simple mechanism of emission and absorption of light by physical matter corresponds to creation and annihilation of photons, which are quantum particles of light. So such processes cannot be adequately handled by a quantum mechanical description of definite number of particles. So we do something called quantum field theory to handle such systems. So what is quantum field theory? It's a huge topic in itself, but as you can see in this Feynman diagram, it represents a particle of momentum p absorbs a photon of momentum q and transforms into a particle of momentum p prime, a defined momentum. And this round blob considers all the processes related to absorption of that photon by the system. So that has a lot of quantum corrections and everything, which is not found in quantum mechanics. So how do we characterize the quantum field theory? That it mostly handles systems which are continuous. It's a generalization of the discrete systems. It definitely can represent infinite degrees of freedoms, and it can have solutions which are actually extended objects, which are not point particles, but they occupy a finite size in space and time. Okay. Before understanding how we go to quantum field theory from quantum mechanics, I must state that we'll take a particular procedure called second quantization, and it depends on the Schrödinger and Heisenberg pictures in normal quantum mechanics. The Schrödinger picture tells about the evolution of a state or a so-called wave function under a Hamiltonian H in time, but the operator is considered to be stationary in time. This subscript S goes for Schrödinger. But there is an equivalent description called the Heisenberg picture, under which the state of the system does not evolve in time, but the operator evolves in time. Here capital H stands for Heisenberg, the subscript. And the exponentiated H is the Hamiltonian. In both the cases, the evolution is unitary. That preserves probability. Now observables, which are the expectation value of some operators, they don't depend on which picture we are handling, because pictures are not physical but observables are, and that's why both the pictures are equivalent physically. But when you have a non-conserved number of particles can get created or annihilated, the Schrödinger picture has a problem. Namely, the state in quantum mechanics represents a definite number of particles. So how do you explain a time evolution under which the number of particles changes? However, the Heisenberg picture, which follows from the Heisenberg equation, does not have that problem, because number of particles or different species of particles are a result of an operator acting on a state. The same operator acts on different states to give you different number of particles. So the operator description remains the same if the particle number changes. So definitely, if you have an indefinite number of particles or the particle number changes, then for such system, Heisenberg picture is a more adequate explanation of time evolution of the system. So if you want to do, or if you want to construct a theory of indefinite number of particles, we will prefer Heisenberg picture. Now, to handle such a generic structure of indefinite number of particles and possibly infinite degrees of freedom, the old description of Hilbert space for quantum mechanics must be generalized to something called a Fock space. What is a Fock space? It is defined by a vacuum or a ground state, and which can generate any number of particles. That vacuum is annihilated by an operator, and which is a generic requirement, because vacuum is the lowest energy state. That means there must be some operator which annihilates it. And to create a particle, there would be some creation operator, which is here A dagger, and it is the Hermitian conjugate of the annihilation operator A. So A dagger acting on the vacuum once creates a one particle state. Then you can define a Hamiltonian operator which actually counts the number of particles, in a sense that the n particle state acted upon by the Hamiltonian will yield the energy En. So H has a structure A dagger A plus V, where V is some constant, and the small v turns out to be the energy of the ground state or vacuum. Now these creation and annihilation operators have a algebra satisfied by themselves, which is called the Heisenberg algebra, which is the A dagger commutator is equal to 1, and that ensures that A dagger will keep on creating particle after particle on acting upon a numbered state, and A will destroy one particle at a time. Now, because of this algebra, if you act A dagger n times on the vacuum, it gives you an n particle state. We'll look at the normalization later of the state, but that is how you define an n particle state. And then equivalently, you can define a number operator, which is A dagger A. This number operator, when it acts on a particle number state n, its eigenvalue turns out to be the number of particle exactly. So the Hamiltonian, as you can see, is linearly dependent on the number operator. So the Hamiltonian also counts the number of particles, and the energy is proportional to the number of particles modulo the ground state energy. Now this kind of algebra you have seen in case of simple harmonic oscillator. So this is the exact simple harmonic oscillator algebra, but here the structure of creation and annihilation operators A and A dagger is not fixed, or it is not given in terms of momentum and position, unlike the simple harmonic oscillator. It can have any general structure depending on the system. So this is a more general description. Now, if you have different numbers of particles of different species, then the vacuum is explained in terms of a tensor product of a number of vacua, and in this case capital N signifies the number of species, which can very well be infinity. In that case, the total Hamiltonian operator is a sum of individual species Hamiltonian, and when this Hamiltonian acts on the vacuum, it gives you just the summation of vacuum expectation values or vacuum energy values for each vacuum for each species. So the summation of vacuum energies can very well be infinite, which is a normal property of quantum field theoretic vacuum, that its energy can be infinite depending on how many species are there. But because we measure energy modulo the ground state energy, this is not a physical quantity that one can observe. Okay, so these species are independent of each other. They individually satisfy the Heisenberg algebra within themselves, and different operator belonging to different species commute. So in general, a state with n1, n2 up to nn number of particles for different species can be written down as that corresponding creation operators up to the suitable power acting on the vacuum and normalize through a suitable constant. So this constant 1 over root over nm factorial is important, which ensures that the probability of the particles found in a particular state is conserved, and also it will be important in the later part of the talk. So what kind of physical system such an algebraic or vector space structure represents? Let's consider two bosons which are non-interacting. Now bosons are represented by symmetric exchange of particles. So a bosonic state of two bosons must be represented by symmetrization of the state. So here eta 1 and eta 2 are observables that label two different particles, and particular values of those observables are labeled as alpha 1 and alpha 2. So in the right hand side you have the symmetrized product of the state where the particles are exchanged, and the normalization required that there is a 1 over square root of 2 factorial factor in front. This state is a quantum mechanical state because these bosons are quantum mechanical particles. They are not second quantized particles. They have definite number, they don't get annihilated or created. Now if you have a number of bosons, a high number of bosons, capital N, which can be infinite also, therein if you have some bosons which are identical, say at once some k bosons are identical, you have to symmetrize their distribution, and then the generic state symmetrized looks like what is given in the right hand side, that this barred state considers k individual bosons which are symmetrized, and that's why this 1 over factorial root over factorial nk is there to take care of this symmetrization. Now this structure is eerily similar to what we saw for a generic n particle state in quantum field theory or in the Fock space. So yeah, this is the definition of this Bart state. So in the Fock space, we had again this the same factor 1 over root over nm factorial for a state where mth state has m number of particles. So there is a correspondence between this nk particles in the Fock space in the kth state and this symmetrized bosonic states of k number of particles which are identical. So there is a one-to-one correspondence. So therefore, these Fock space states can be thought of as bosonic excitations, and in general, if you consider a variable number of particles in the system, that 1 particle Bose state, 2 particle Bose state, 3 particles Bose state, or even 0 particle Bose state, all of them can be combined to be given a variable number of particle state in the Fock space, which is in the left hand side. Consider the summation over m there, which represents all the possible total number of particles in the system. And how they are connected together, that means how bosonic operators or bosonic observables are connected to the Fock space observables. So this is the mapping. Here eta I are individual boson operators in the quantum mechanical bosonic space, and their summation is eta b, which is the total operator in the bosonic space. In the right hand side, eta f is the fermionic operator that corresponds to eta b, which is just a summation of some linear combination of a bigger m and a n, where m and n are levels of different states in the Fock space. So eta mn is the corresponding coefficient in the Fock space, but this coefficient is defined as expectation value of eta I in the bosonic space. So that is the connection, that eta i's in the bosonic space are related to the coefficients eta mn in the Fock space. And mind you, this summation in the bosonic space goes up to capital N, which is usually finite, but in the fermionic state, in the Fock space, the summation goes up to infinity because there are infinite states possible. So that's why this mapping is only one way, from single particle bosonic space to the Fock space. Okay. So this physically means if you take the expectation value of eta b in the bosonic space, and if you take the expectation value of eta f in the Fock space, they must be equal. And it so turns out that they are equal just because we have a map between eta I and eta mn. Okay, so that means that we represent bosonic excitations in Fock space as particles, and that is the interpretation of the particles in a second quantized theory. So in the same way, we can represent interactions which will have two body operators, and in the Fock space they are represented as a combination of two creation operators and two annihilation operators. Then you can construct three body operators in the bosonic space, which will correspond to three creation operators and three annihilation operators in the Fock space. All these 1 particle, 2 particle and 3 particle operators, they commute with the total number operator. That means that because they map from a bosonic space where the particle number is conserved, in the Fock space also for such operators, the corresponding number of particles will be conserved. So this is simply a one-to-one correspondence. But where the Fock space becomes more general is that in Fock space we can define operators which are combination of, say, 2 creation operators and one annihilation operators. This represents a process where one particle is getting created by its own. So definitely the number of particles is not conserved. That's why this corresponding total operator CF does not commute with the total number of operators in the Fock space, and there is no analog of this operator in the bosonic space. So although these particles are actually of bosonic nature in the Fock space, there can be situations or there can be structures you can construct which represent processes like creation and annihilation of particles which are not present in the bosonic space, which is a quantum mechanical space. So that's how the Fock space is more general. And finally, in the bosonic space, you can define a change of basis, like from eta basis, you can go to some xi basis like this. And because these eta states corresponds to creation operators in the Fock space, that will imply that the creation operators also can change. And similarly, the annihilation operators can also change under a basis transformation like this with the same coefficients. So that means the operator coefficients in Fock space correspond to the states in the bosonic space. So indirectly here we can see how the so-called field theory arises. Because these creation and annihilation operators in Fock space, they can have any values, their labels can vary continuously. What I am saying that K can have values which are very close together. They can represent even momentum physically. So they have a continuous description. They can have continuous description, and because of that, they are representing particles which have continuous distribution. That is not the case in the bosonic sector or in the quantum mechanical space, where these particles can have definite quantum distributions only, which are discrete. And more so, the nature of bosonic state is represented by these expansion coefficients, which can also be continuous. Okay, for fermions, we have to construct a different Fock space which will correspond to quantum mechanical fermionic space, but that will be explained in terms of anti-commutators, not commutators, but it will have a similar kind of structures. So that's how from quantum mechanical particles we come to a field theoretic structure. And why this system is second quantized? That is because quantum mechanical operators were already quantized, but the states or the wave functions were continuous. Now they map to these coefficients of creation and annihilation operator, which are again quantized. So this is the second quantization. So the basic concept is that operators transform like states, and that is where the whole second quantization manifests in the Fock space. So finally, we can summarize as that many-body systems or quantum mechanical systems are represented by operators, individual operators. They represent definite particles, and this particle numbers is usually finite. So these operators, when we go to the second quantized Fock space, these operators corresponds to the coefficient of this creation and annihilation operators, and they represent excitations in a Fock space of a bosonic field. So that is the definition of particle in a field theory or a second quantized theory, that they are the excitations of a field which correspond to particles in a first quantized theory. Now the particle number and degrees of freedom can be indefinite because Fock space has the additional property of creating and annihilating extra particles, which is not possible for a many-body first quantized scenario. So hope this talk gave you some idea about how to come from first quantized to second quantized theory. There is an easier and an independent approach of taking a classical field theory and quantize it once to arrive at a quantum field theory. But this present approach shows how we directly go from a first quantized theory to a second quantized theory, and what do we mean by second quantization, and why Fock space is important, and it's a generalization of a Hilbert space of a first quantized theory. So thank you very much for listening. Until next time.